Solution stoichiometry is no joke. It's quite a bit of work, but luckily we've laid the groundwork with our regular stoichiometry, and the process is exactly the same. And now we get a major payout from the way that I have forced you to set up your stoichiometry problems up until this point. And what I mean by that is setting up completed balanced chemical equation, what you have and need in moles to get an excess and a limiting, getting your amount excess by subtraction, getting your theoretical yield, and all that. So I know there are many other ways to set up stoichiometry problems. I've done it this way, and now it's about to pay off because our solution stoichiometry gets a little more complicated. The good news is it's still stoichiometry. And what that means is we still need mole ratios from the balanced chemical equation, which means we need moles at some point in time. Other ways that we've seen stoichiometry so far, we've seen it given as straight up moles, or we've seen it given as, so for example, we've seen it given as moles. We've seen it given as mass, which we then divided by molar mass, and that gave us moles. And now we're going to end up seeing concentration and volume, which we're going to use to get moles. All right. So the unifying theme there among all of our stoichiometry problems is moles. So we need to either be given moles, or to turn a mass into moles, or to turn a concentration and a volume into moles, and everything in between is exactly the same. So I'm going to start us out with a complete stoichiometry problem, and then we're just going to tack on at the beginning and the end these little pieces. In other videos we've done mountains of stoichiometry problems, and I don't think there's any benefit in this case for us to slowly go through step by step. What I'm going to do instead is pause the video, write out a step, and then we'll skim what I did in that step, and then we'll focus on the outer parts, what actually happens when we have a concentration and a volume. So a quick note here, I've started the problem, 0.03 moles of lead nitrate, 0.09 moles of sodium chloride, 8 grams of precipitate collected in lab. We need a completed and balanced chemical equation, and that's something we've written out a million times, and I'll go ahead and write it out right now. Alright, there's our completed and balanced chemical equation. I snuck in those phases that I pulled up from our solubility rules. Nitrates tend to be soluble. Sodium group 1 metal or chloride without lead, silver, and mercury tend to be soluble. Chloride with lead insoluble. Sodiums or nitrates aqueous. We need to identify the limiting reactant and the excess reactant. We'll do that by comparing these amounts that we have to each other. I will see you momentarily. I set this up with what I have, these amounts that were given here, did our comparison of reactants to each other. In this case, we find out that we need 0.0600 moles of the sodium chloride, 0.0600 moles of sodium chloride, and we need 0.0450 moles of that lead nitrate. Comparing our halves to our needs right here, you can see we have 0.03 moles of the lead nitrate. We need 0.450. We don't have enough. So this becomes our limiting reactant. We don't have enough of it. And we have 0.09 of the sodium chloride, and we need 0.06. That is more than we need, which means that this is our excess reactant. And that gives us our answer to part B. Also take note, I really poorly planned my space budgeting and had to move need over. Now we need to find out about our amount excess. We get our amount excess by subtracting what we have of the excess, that's 0.09, and what we need of the excess, that's 0.06, and we end up with 0.03 moles of NaCl excess. Done, done, done. Time for a theoretical yield. We'll use the limiting reactant and compare it to our products to get our theoretical yields. Our limiting reactant was the lead nitrate. Our chemical equation tells us 1 mole of lead chloride for every 1 mole of lead nitrate. 1 and 1 gives us 0.03 moles of lead chloride, theoretically. And 0.03 times 2, because there's 2 sodium nitrates, gives us 0.06 moles of sodium nitrate. None of this is new at this point. We also need to get a percent yield, and we were given an actual yield right there. Now, my solid product is the lead chloride. which has a molar mass of 278.1. And you could calculate that. I just happen to have written it down in advance. For a pencil. Here we go. The molar mass is 278.1. So I'm going to take that number down here. I'm going to multiply by 278.1 grams per mole, and that's going to give me a theoretical yield in grams for that product of 8.34 grams, I believe. 8.34 grams PbCl2. And that's also part of our answer to D there, our theoretical yield. But the reason we need it right now is so that I can get my percent yield, letter E. And we know, again, how to calculate that. I'll be right back. Here we have our calculation of percent yield, 8 grams as the actual yield, which we got from up there. I don't know that it has any benefit to me highlighting that stuff, but we can try. So the 8 grams was our lead chloride, and that's what we put right there. And then the 8.34 grams was our theoretical yield, and we put that right there. We ended up with 95.9% yield. Now, we've got some room over here that I have wasted up until this point, and that's because there's something we didn't do. This pen's been sitting here covering up the concentration of ions in the final solution. This is the real trick, all right? So we're going to take care of that, and I'm actually going to jump back and show you what's under this tape here. There's nothing special under this tape. I just didn't want to use a different piece of paper, and I had to cover some stuff up. But let's take care of this. This is a super legit question that comes full circle with one of the videos I did a couple times ago. And that video dealt with aqueous reactions, specifically double replacement, and what is present in the final solution. All right, so hopefully this is on the screen. Aqueous product and excess reactant. When you react these things, aqueous and aqueous, beaker full of ions, you mix them together, some of the ions are left over, those are spectators, and something has been produced. In this example back here, it was solid silver chloride. And then if you have excess, you end up with some of those ions left right there as well. So this bit of information is absolutely critical for us. In fact, I'll take these words and write them right here. And if you want more detail on that, go ahead and jump back to that video, which is in this same playlist. In the final solution, we are looking for our aqueous product, and we're looking for any excess reactant. And luckily, we know what those things are and where to find them and how we're going to label them. Green highlighter has already been used, but let's take a look here. For our aqueous product, what is our aqueous product? It is the sodium nitrate, all right? And what is our excess reactant? Our excess reactant is this NaCl. I'm hesitant to go green over, orange over orange. So this number right here is our excess reactant. And those are the ones we need to deal with. Now let's take a look at some of the other tools we have. Oh yeah, right? This is NaCl in water. It's a strong electrolyte. It would dissociate. Remember, this is a double replacement reaction. We would dissociate anything that's aqueous. Well, let's show reality right there. And that reality is times 1 times 1, because it's a 1 and a 1. And if you're not sure about that, I've got a playlist video that goes along with that for our molarity calculation examples number 2 and 3. It's stoichiometry, but it's super cheap. Subscript, subscript, multiply, that's how you get those numbers. Subscript, subscript, multiply, that's how you get those numbers. And that is what I'm going to do here, times 1 for the sodium, 0.03 moles of sodium ions, that's 0.0300, 0.0300 moles of chloride ions. This, my friends, is absolutely critical information. This is from my excess. It's not the answer to anything, but it's numbers that are going to get us the answer we need. So this thing that I'm highlighting in purple right here, That's new. We've never done that before in one of these problems, so that's why I'm trying to make this pop on the page a little bit. The other thing we're interested in is our aqueous product. Our aqueous product is the NaNO3. NaNO3, aqueous. We're going to dissociate it the same way we just did. Sodium, we have one of those. And nitrate, we have one of those. So I'm going to end up with 0.0600 moles of sodium ions and 0.0600 moles of those nitrate ions. This is not the answer to anything, but it's something we desperately need. And this is from our aqueous product. So I'm going to highlight that just like we did there, because this is something we have not done before in a stoichiometry problem. Identifying from our excess and from our aqueous product tells us what's in the final solution. In fact, let's continue our highlighting a little more. Our excess was the sodium chloride, and our aqueous product was the sodium nitrate. Those are the things that are in my final solution. All right, so let's list that out. What do I have in the final solution? And boy, is my color coding out the window at this point. In the final solution, I've got aqueous product and excess reactant. What do I have from my aqueous product? I have sodium ions. I have nitrate ions. What do I have from my excess reaction? I have sodium ions. And I have chloride ions. And what you might notice here is I listed sodium ions twice. I don't need to do that. I'm just going to have to note that these things the sodium ions come from two places. In fact, when you see me do these problems, you'll see me label off to the side. And this is not part of the answer, but again, I feel like it's good bookkeeping. Label where they come from. Where do the nitrate ions come from? The nitrate ions come from my aqueous product. Where do the sodium ions come from? They come from my aqueous product and from my excess. So product plus the excess. And then where do the chloride ions come from? They come from the excess. Now, again, that's not part of the answer, but I find it to be good bookkeeping. We're trying to find concentrations of these things. Concentration as molarity, moles over volume in liters. So we're going to need our denominator. These are molarities that we're looking at. That's moles of our solute over the volume in liters of the solution. And we can copy these numbers over from these charts right here, and I'll try and be a little more clear with my colors. All right, nitrate ions from the excess, from the product, we've got 0.0600 moles. So 0.0600, that is from right there. Sodium ions we get from the product 0.06, and we also have 0.0300 moles. From our product we had 0.06, and from our excess we had 0.03. For the chloride ions, from our excess we just had 0.0300 moles. All right, so all those numbers are moles. We need a volume in liters of the solution though. There is information under this tape that I didn't mention previously, and let's take a look at what that is. 0.03, 0.09. It was really a volume and a concentration and a volume and a concentration. So take note, this 3 times 0.1 gives us 0.03 moles, and 3 times 0.3, or rather 0.3 times 0.3, 0.09 moles. So our total volume, total, is just going to be the volume of the first thing plus the volume of the second thing. And those were 300 milliliters plus 300 milliliters. which is 600 milliliters, and we need that in liters, which is 0.600 liters. So this will be 0.600 liters, 0.600, and 0.600 liters. Just so we can keep track of those, this 300 and this 300 came from this 300 and this 300. All right, so that is where that came from. We were given some starting amounts. And you initially couldn't see that because I had it covered up with tape, but that was the information that was underneath. I just wanted you to feel like it was a standard stoichiometry problem. Let's get these answers here, and we'll fill in one tiny thing and move on with our lives in this problem. 0.06 over 0.06 for the nitrate ions gives us 0.100 molar NO3 minus. Okay, for the sodium ions, you've got 0.09 over 0.6, which gives you 0.150 molar sodium ions. And then for the chloride ions, we've got 0.03 over 0.6, which ends up being 5.00 times 10 to the minus 2 molar Cl minus. And I switched that to scientific notation because we had a number less than 0.01, and I wanted to make sure that would work out. So this is letter F, the concentration of our species present in the final solution. Now, let's go back in time for a moment. To that, I wrote down 0.03 and I wrote down 0.09, but what if I hadn't been given 0.03 and 0.09 and I had instead been given 300 mils of 0.1 and 300 mils of 0.3? And the answer is no problem. Since molarity is moles over volume in liters, I'll write that equation somewhere. Molarity equals moles over volume in liters. And I know a molarity and a volume in liters, so I can get moles as my molarity times my volume in liters. And so for this first one, we had 0.1 times 0.3. And for this other one here, we had 0.3 times 0.3. And that gave us the 0.09. So I gave you a false sense of confidence by just starting you out with moles, but it just took this much more work to take care of it if it didn't start out in moles. A through E were all the same. We just had this new special letter F, concentration of ions, which was based on these right here. So I realize it feels a bit overwhelming. Just keep in mind, all that stuff's the same. The amount excess we dissociated, the theoretical yield aqueous we dissociated. We got a total volume, and then we just did some division. And we'll see several more of these examples.